In this video, we solved problem 13.9.023 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following. We've got four ordered pairs, 0, 6, 4, 5, 4, 3, and 5, 0. I've labeled them x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, and x sub 4, y sub 4. In part A, we're asked to find the least squares regression line. That's a line. It's just going to be in the form y equals mx plus b. We're going to use different letters though. We're going to use f of x or y equals ax plus b. We're going to find that value for a and find that value for b. That will give us the least squares regression line for these points, for this data. Now, we say that this regression line is the least squares regression line if A and B are chosen to minimize the sum of the squared errors. So let's write that down. And an error is just the difference between the y value that is predicted by this line and the actual y value in a particular ordered pair. So if this is our predicted y value, y predicted is going to be ax plus b, and the actual y value will be the y value in this ordered pair over here. Now we want this to be our error at each of these points, x sub 1, y sub 1, x sub 2, y sub 2, all the way through x sub 4, y sub 4. So I will say that this is the ith error, and I'll plug in x sub I here and y sub I. So I will go from 1 to 4. And we want the sum of the squared errors to be as small as possible. We want to choose A and B so that the sum of the squared errors are as small as possible. So that's our error, the sum of the squared errors. We can think of that like this. Now, x sub I and y sub I are known because we actually have values for x sub I and y sub I for I equals 1 through 4. So this sum of the squared errors is going to be a function of two variables, a and b. A is the slope of our regression line. B is the y-intercept of the regression line. And in our case, we've got 4 error terms because we've got 4 different points. So we're going to take the sum as I goes from 1 to 4 of this difference. That's our error squared. We want that to be as small as possible. We want to choose A and B to make that as small as possible. That's actually not too difficult to do. If I want to make this function of two variables as small as possible, I can just use the second partials test. Now, if we want to, we can actually plug in our x sub I and y sub I as well. So we're going to have a times x1 plus b minus y1 squared, a times x sub 2 plus b minus y2 squared, a times x sub 3 plus b minus y sub 3 squared. And then the last one is going to look just like the others, but with x sub 4 and y sub 4. Now, what I want you to see is that these are differences between y values. This is the y value predicted by this line, and this is the actual y value in our ordered pair. Now, x sub 1, y sub 1 was the point x equals 0, y equals 6. So I will substitute that in here. And x sub 2 was 4, and y sub 2 was 5. So I'll have 4a plus b minus 5, quantity squared. X sub 3 was 4, and y sub 3 was 3. and x sub 4 was 5 and y sub 4 was 0. Okay, so this is the function that we're trying to optimize. It's really not too bad. We just got to do a little bit of partial differentiation. We know that if we want to optimize a function of two variables, the first thing that we need to do is find the critical points for this function. Well, first thing we need to do is come up with the function itself. And then we need to find its critical points. So we've got our function. So we want the gradient of this guy to equal the 0 vector, which is the same as saying that the partial of s with respect to a must be 0 at the same time that the partial of s with respect to b is 0. So let's compute the partial of s with respect to a. This has no a's in it, so we're going to get 0. This one does have an a in it, so we'll have 2 times the quantity 4a plus b minus 5 times the derivative of the inside with respect to a, which is 4, treating b as a constant. This one has an a in it, so we'll have 2 times 4a plus b minus 3 times the derivative of the inside, which is 4. And this one has an a in it, so we'll have 2 times 5a plus b times the derivative of the inside, which is 5. So if we simplify that, we've got 8 times 4a plus b minus 5 plus 8 times 4a plus b minus 3 plus 10 times 5a plus b. And if you want, you could, simplify further. Just distribute. Okay, so I've got 32a and 32a, that's 64a. 64a plus 50a is 111, or 114, excuse me. Yeah, 64 plus 50. And then, so that's that. And then we've got the b's. We've got 8b plus 8b plus 10b. 16b plus 10b is 26b. And then we've got a negative 40 minus 24, so that's negative 64. So we need this function to be 0. And at the same time, we need the partial of s with respect to b to be 0. So let's take these derivatives with respect to b. This has a b in it, so we're going to have 2 times that quantity. This is just the power rule, times the derivative of the inside by the chain rule, which happens to be a 1. And the same is true there. 2 times the expression in parentheses times the derivative of the inside, which is 1. I think we get that for all of these because they all just have a plus b inside. Okay, and then we can distribute. So this is 2b minus 12 and 8a plus 2b minus 10 and 8a plus 2b minus 6 and 10a plus 2b. Let's see how many a's we have. 8a plus 8a plus 10a, 16 plus 10 is 26a. And then we've got 2b plus 2b is 4b, 6b, then 8b. And we have a negative 12 minus 10 is negative 22. Negative 22 minus 6 is negative 28. Okay. And we need these two functions to be equal to 0 at the same time. So you've got 2 equations and 2 unknowns. You're trying to solve for a and b. So you have 114a plus 26b minus 64 equals 0. If I add 64 to both sides, I'll have that. And then on this one, we've got 26a plus 8b equals 28. If you want, you could maybe divide everything by 2, divide everything. Yeah, I think that might make our lives a little bit easier. But we could also just start multiplying. I'd really like to get rid of the b's. So to get rid of the b's, I think I'll just multiply this equation by -8, and I'll multiply this one by 26. Excuse me. And let me make sure I write my problem down correctly. So if I call this equation 1 and this equation 2, we're going to take equation 1, we're going to multiply it by -8, and then we're going to take equation 2 and multiply it by +26, and then we'll add them together. And I'm writing them, I'm going to stack those two equations vertically and then add vertically. To simplify my life, I'm going to use the calculator for the arithmetic. So I have 114 times -8. So it's -912 times A. And then we have 26 times 8 is, and then it's going to be negative. We'll have -208 times B. And 64 times 8 is 512. It's going to be negative. Okay. And then down here, we're multiplying the equation by 26. So we have 26 times 26, or 26 squared, which is 676. And then we'll have 26 times 8, which should be 208. If I typed it in correctly last time, yep. And then 26 times 28, 728. When we add those together, we should get rid of the b's, and we do. So I have -912 plus 676, which is -236 times A equals this quantity, 728 minus 512. Oops. Now I get 216. And then to get A by itself, we'll just divide. So we get 54 divided by 59, or -54 divided by 59 as our A value. Okay, so now that we have A, we can use A to find B. Just substitute your A value into one of those equations and solve for B. I think I'll take the second equation. So we'll have 26 times A plus 8 times B equals 28. So we'll have 8B equals 28 plus 26 times 54 over 59. Oops, I typed that incorrectly. 54 divided by 59 times 26 plus 28. That's this quantity over here, and then we're going to divide it by 8 to isolate B. And we get 382 over 59. Okay, so that is the one critical point. And we're hoping that that is the A and B that will minimize the sum of the squares. And I think we can tell that this quadratic type form, if we expand all of this, we're going to have squared terms involving A and B. It's going to have a minimum, not a maximum, because all of these terms are 0, or at the smallest they could possibly be, a squared number would be 0. So these are going to be greater than or equal to 0. Since they're the errors, they're the difference between the y that's predicted by our regression line, that's the line of best fit that's going to go through those points. There's probably not going to be 0. It's going to be some number that's greater than 0. Or the error could be positive or negative, depending on whether the line is above or below the point. But then when you square it, that's going to be positive. So this is a positive number. A positive number is a positive number and a positive number. So this is going to have a minimum when I take all of those squared errors, not a maximum. If you're saying to yourself, how do you know, how can you prove that this particular critical point corresponds to a minimum and not a maximum? Remember how we do that? We use the second partials test. Or in other words, we can find the Hessian matrix. This is the matrix of second partials, second partial derivatives of our sum of the squared errors function S. And it's actually pretty easy to find. The second partial of S with respect to A is 114. So the derivative of that with respect to A is 0, and the derivative of that with respect to A is 0. Now, the second partial of S with respect to A and then B should be the same as the second partial of S with respect to B and then A. The derivative of this guy with respect to B, treating A as a constant, is just a 26. And hopefully the derivative of this guy with respect to A, treating B as a constant, is 26, and it is. So those are both 26, good. Should be the same, we expect them to be the same. And then the second partial of S with respect to B comes from taking this partial of S with respect to B and taking its derivative with respect to B. We're going to get 0 there and 0 there because those have no B's and we're treating them A's as constants. And the derivative of 8B with respect to B is 8. Okay, so that's our Hessian matrix. If we take the determinant of that at our critical point, that's going to tell us whether that critical point corresponds to a minimum or a maximum, or a saddle point. And we think it's a minimum because we saw all those squared expressions. We have this times this minus that times that. And we don't even really care about the value of this. We just want to know, is it positive or is it negative? It's positive. If that determinant is positive at the critical point, what that's telling you is that locally, this surface looks like an elliptic paraboloid, either facing up or facing down. To figure out whether it's an elliptic paraboloid or if it's similar to elliptic paraboloid facing up or facing down, in order to distinguish between those two, we look at the signs of the terms on this diagonal. So we've got D is positive, so that means we have a min or a max, and the second partial of S with respect to A at our critical value, I'm just going to call it A naught, B naught, is 114, which is positive. That means that this surface is concave up in the A direction. And it's also concave up in the B direction. So since it's concave up in both directions, what we have locally, it corresponds to a minimum. So S of A and B has a relative minimum at the critical point, which is given by those fractions there. Okay, so we know that that has a relative minimum. We were trying to minimize the sum of the squared errors. This is where the minimum occurs. Now that we know what A and B are, we can substitute those in over here, and that is what's called the least squares regression line. So y is going to be equal to ax plus b, where a was negative 54 over 59, and b was 382 over 59. Okay. Then it says calculate S, the sum of the squared errors. Well, all you do for that is you substitute in your A and your B into this function right here. So I'm going to keep that function nearby so that I can plug my A and B into it. S evaluated at A equals negative 54 over 59 and B equals 382 over 59. It's going to be equal to our B value, 382 over 59, minus 6 squared plus 4 times A plus B minus 5 squared plus 4 times A plus B minus 3 squared plus 5 times A plus B squared. It's tedious, but now you just want to enter all of those into your calculator, making sure that you didn't type anything into your calculator incorrectly, and evaluate that expression. So I'm going to pause that while I type into my calculator, and then I'll write down the answer. Okay, so after I did all of my typing, I got 510 over 59. And just to get a decimal approximation, that's approximately 8.64 units. Now, just to see what we actually obtained here, let's actually graph that line along with these points. And then we'll talk about this sum of the squared errors as we're looking at the graph of the line. Okay. So here's Desmos, and I've plotted the points already. Now I want to graph f of x equals negative 54 over 59 times x plus 382 divided by 59. And that's it. That's the sum, or that's the least squares line. Now, it's a little bit hard to see, but the errors are the difference between this predicted y value on the line and the actual y value in the ordered pair. So this predicted y value on the line is 6.475. So if I take that y value and I subtract this y value, that's going to give me 0.475. Now over here, at x equals 4, let's see what f of 4 is. So f of 4 is approximately this 2.8135. So the errors here are this y value of 5, or it's the difference between this y value of 5 and the y value on the line, this y equals 2.8135. So I'm taking the predicted y value of 2.8135 approximately, and I'm subtracting 5. That's an error. And then we're also going to take the predicted y value and subtract the y value on this point, 3. And we're going to take those errors and we're going to square them. And then over here at x equals 5, the predicted y value turns out to be 1.8983. It's very different from the actual y value associated with x equals 5, which happens to be 0. But we're going to take this y value of approximately 1.8983, and we're going to subtract 0, and then we're going to square that. So if we take that difference and we square it, and we take that difference and we square it, and we take that difference and we square it, and we take this difference and we square it, and we add them all together, what we get is this S, the sum of the squared errors, that 510 over 59, which is approximately 8.64. What this is saying is that this is the line, this black line that we have drawn here. This is the line that makes that sum of the squared errors as small as possible. I could not choose another line to make the sum of the squared errors less than this 510 over 59. It's not possible. If I draw any other line through the XY plane, and then I look at the squared errors, the squared errors are going to have a sum that's greater than 510 over 59. So that's what we're doing. This is the best fit line in the sense that it's minimizing that sum of the squared errors. And that's how we do that.